Problem 15. We're given 3 points A, B, and C, and we want to find the distance from the point B to the line going through the points A and C. So there is a line, here is A and here is C, and here is the point B. We want to find how much is this distance. Okay, so what are we going to do? This is the point A, this is the point C. We can define the vector AC, and the vector AC is 1, minus 3, negative 2, 0, minus 1, negative 1, 3, minus 1, 2. And we also have to define the vector AB, so that we're going to project the vector AB onto AC. So AB is equal to 2 minus 3, negative 1, 1 minus 1, 0, 3 minus 1, 2. Okay, so we project AB onto AC. That's AB dot product AC dot product, it's a scalar, over AC dot product AC times the vector AC. So I have a ratio of two constants, which is a constant times AC. So AB times AC is negative 2 times negative 1 is 2. Negative 1 plus 0 is 0. 2 plus 2 is 2. Divided by AC dot product AC. So that's negative 2 squared plus negative 1 squared plus 2 squared times the vector AC, negative 2, negative 1, 2, giving us 4 over 4 plus 4 is 4 plus 4 is 8 plus 1 is 9. Here I think I made a mistake. AB dot product AC, negative 2 times negative 1, 2. This is 0. 2 times 2 is 4. Sorry about that. So this is 6 times negative 2, negative 1, 2. Okay, so this here projection, let's call it, I don't know, U. So this is the vector U, is equal to 6 over 9, that's 2 over 3 times negative 2, negative 1, 2. Okay, so how much is this distance going to be? Well, if I find the difference between AB minus U, right, I'll get this vector right here, and its magnitude is going to give me the length, so the magnitude of this vector. So AB is the vector negative 1, 0, 2, minus 2 over 3, negative 2, negative 1, 2. That's equal to negative 1 plus 4 over 3, 0 plus 2 over 3, and 2 minus 4 over 3. So this is 1/3, 2/3, and 6 minus 4, 2/3. And that's the square root, so now I'm looking for the magnitude of 1/3 squared plus 2/3 squared plus 2/3 squared, which gives me the square root of 1 over 9, excuse me, plus 4 plus 4 over 9 plus 4 over 9, that's 9 over 9, and that's 1, and square root of 1 is 1. Okay, so basically this vector here is the unit vector. There is one unit distance from the point B to the line passing through A and C. There is another way how you can evaluate this. If you consider this parallelogram, so let's sketch just another. So C, A, and the B. Okay, so the area of this parallelogram is the height h times the norm of the vector AC, right? So h times AC. On the other hand, that's also equal to the norm, right? How do we find parallelogram? Defined by these two vectors AB and AC. That's the norm of AB cross product AC. But as you can see, this h is actually the distance from B to the line AC. So you can go through the cross product if you want. Okay, so this h, or our distance, right, is equal to the norm of AB cross product AC over the norm of AC. Okay, what is AB cross product AC? So right here, so that's the norm of the vector -1 times 2, that's -2 minus 0, minus -2 times 2 is -4, minus -2, that's -4, so -2 times 2 is -4, minus 2 times -1, that's -2, so that's -4 plus 2, it's -2, but be careful, here I have minus, so minus minus 2, which is 2, and finally -2 times 0 is 0, minus -1 times -1 is 1, so minus 1. Over the norm of AC, so that's the square root of -2 squared plus -1 squared plus 2 squared is equal to the square root of -2 squared plus 2 squared plus -1 squared over square root of 4 plus 1 plus 4, and as you can see, you have square root of 9 over square root of 9. Again, you have the distance or the height is equal to 1. So in both cases, you get the same answer. You don't have to do both of them. You just have to do one approach, either through the projection, which involves the product rule, the dot product, or through the cross product. Part B says find the point on the line containing A and C that it's closest to B. So basically, this is the point that I want to know. How much is this point? Okay? So A, C, and here is B. And we found this vector here. So let's call this point M. And I want the coordinates of M, X, Y, and Z, right? Well, I have the vector AM, which is the U vector found in the projection, the U vector found in part A. So that's equal to -4 over 3, right? -2 over 3 and 4 over 3. But also this vector is the terminal point of the vector M, so that's X, Y, Z minus A. And the coordinates of A is 3, 1, and 1, which can be written as X, Y, Z minus 3, 1, 1. Okay? If I take this term and bring it on the other side of the equation, I get the coordinates of M. So X, Y, Z is equal to 3, 1, 1 plus -4 over 3, -2 over 3, 4 over 3. And that's how much? 9 minus 4, that's 5 over 3. 3 minus 2, that's 1 over 3. And that's 7 over 3. Okay, so that's the point. M has coordinates 5 over 3, 1 over 3, 7 over 3. Part C says find the cosine angle formed by A and B. Okay, so this formula, we know that it's being used quite a lot. AB dot product AC is equal to the norm of AB times the norm of AC times the cosine theta, and theta is this angle right here. Okay. Always make sure that maybe some of these values are already found. You have already found these values. So AB dot product AC, AB dot product AC is 6 from part A. AB dot product AC. The norm of AC is the square root of the dot product AC dot product AC, right? So the norm of AB is square root of -1 squared plus 0 squared plus 2 squared times AC is, as I said, where is AC? -2 squared plus 1 squared plus 2 squared times cosine theta. So we have 6 is equal to 1 plus 4 is square root of 5 times square root of 4 plus 4 is 8 plus 1 is 9 cosine of theta. So cosine of theta only is equal to 6 over square root of 9 is 3 times square root of 5, or that's 2 over square root of 5, or 2 times square root of 5 over 5. These are identical expressions. And finally, question D. Find the area of the triangle with vertices A, B, and C. So A, B, and C. Okay, we know that this area right here, the area of the triangle is 1/2 the area of the parallelogram, and that area is being found as the norm of AB cross product AC, but we already did that in here. If you haven't done it then you will do it. The norm of AB cross product AC was square root of 9, so that's 1/2 times square root of 9, so that's 3 over 2. Okay, question 16. So we have 2 points L1 XYZ is equal to 1, 2, 2 plus S 1, 0, 2, and the line L2 XYZ is equal to 3, 1, negative 1 plus T negative 1, 1, 4. Okay, so you need the normal equation of the plane that contains L1 and it's parallel to L2. So I want this, let's call this plane here, whose equation I want. So that's AX plus BY plus CZ is equal to D. I want to find A, B, C, and D. Okay, in which, so what does it say? Find the normal equation of the plane that contains L1. So L1 belongs to this plane, and then you have L2 here that's parallel to the plane. Okay, so what are we going to do? What is our approach? This L2 is parallel to some vector here. Okay, and that vector is negative 1, 1, 4. Okay, this vector can be translated, can travel through the space, and we'll call the vector will be the same as long as its direction and as long as the direction and the magnitude are the same. So basically I can take that vector and translate it here, put it on the plane, negative 1, 1, 4. On the other hand, L1 is parallel to the vector 1, 0, 2. Once I have two vectors on the plane, I can find what? I can find the normal vector. And the normal vector will give me the values of A, B, and C. Well, how much is going to be the normal vector? The normal vector is just going to be 1, 0, 2 cross product negative 1, 1, 4. Now, of course, you can go through, you can write this as the determinant of I, J, K, 1, 0, 2, negative 1, 1, 4, or if you are already equipped with, if you have practiced enough, then this is just going to be, right, cover the first row here. My light is a little bit off. And you have 0 times 4 is 0, minus 2 times 1 is 2, minus the second entry, 1 times 4 is 4, minus 2 times negative 1 is negative 2, so minus negative 2 is plus 2, and finally 1 times 1 is 1, minus 0. So you get the vector negative 2, negative 6, 1. which means what? Which means that you have obtained the values of n, right? And now what is the equation of a plane? It's the normal vector dot product x, y, z minus x naught, y naught, z naught is equal to 0, where x naught, y naught, z naught is a point on the plane. Okay, well, again, I look at L1, okay, and from the equation of L1, since L1 lies on the plane, that means that this point also lies on the plane. So this is the point 1, 2, 2. So basically, I have the normal vector -2, -6, 1, dot product x minus 1, y minus 2, z minus 2 is equal to 0. Now calculate this dot product, -2, x minus 1, minus 6, y minus 2, plus 1 times z minus 2 is equal to 0. -2x plus 2 minus 6y plus 6z, oh sorry, plus 12, that's a 2, not a z, plus 12 plus z minus 2 is equal to 0. -2x minus 6y plus z is equal to 2 and -2 cancel out, is equal to -12. So there you go. This is the equation of the plane. Or if you want, you can multiply everything by -1 and get 2x plus 6y minus z is equal to 12. Absolutely the same. So just to recap what happened, I took this vector parallel to L2, and because L2 is parallel to the plane, that means that this vector, when translated, will land on the plane. Once I have two vectors spanning the plane, right, their cross product is going to give me the normal vector, and here I evaluated the normal vector, and then I just jump into figuring out the equation of the plane by this formula. That's the normal vector dot product xyz minus x naught, y naught, z naught, where x, y naught, y naught, and z naught is a point on the plane. Since L1 belongs on the plane, that means every single point on L1 is also on the plane. Well, explicitly, from the formula of L1, explicitly, it is given what point is on the plane. You can take any point here for any given s, but why bother when this particular point is given to us, 1, 2, 2. So I plug it right here, 1, 2, 2, and then just evaluate this dot product and express it in the form that we're being asked to express the equation of the plane. Problem 17. We're given a set consisted of two-dimensional vectors for which the following condition is satisfied. What did I say? Similarly to transformations, with these sets, it's always a good idea to check, to just before even reading the question, what does it say? Check what type of vectors are in here. Okay, so let's write one or two vectors. Okay, so for example, 0, 0 is in this set, because 0 squared is equal to 4 times 0 squared. What else? If you take -1 for x, -1 squared is 1 times 4 is 4, right? So y squared is equal to 4. That means 2. Okay, but also if you take -1 for x, -1 squared is 1 times 4 is 4, square root of 4 is also -2. But also if you take x is equal to 1, 4 times 1 is 4, square root of 4 is 2, so 1, 2. Also 1, -2, and so on and so on. If x is 5, 5 squared is 25, so 5, times 4 is 100, so y can be 10, but also it can be -10. And so on and so on. Okay, so the first question, A, determine whether this set is closed under vector addition. So let's check for any of these two, right? So let U is equal to, be careful, you're choosing vectors that are already in V, checking whether their sum is also in V. So negative 1, 2, and V, let's take negative 1 and negative 2. Okay, so U plus V, it's simple addition, that's negative 2 and 0. Is this also in V? This is not in V because y squared is 0 squared is not equal to 4 times negative 2 squared. Hence, V is not closed under vector addition. Part B, well, if I multiply this vector by any constant, right, taking this into account, right, if I get here c squared and if I get here c squared, the same constant, that will cancel, will bring me back to this equation that is already satisfied by assumption. So my guess is that this is closed under scalar multiplication. So I take a vector from V, for which that means that this is satisfied. Okay? Then I check whether C times xy is in V. Okay, well, C times xy is equal to Cx Cy, and this will be in V if Cy, the whole thing squared, right? The square of the second entry is equal to 4 times the square of the first entry. So let's see whether this is satisfied. C squared y squared is equal to 4 times C squared x squared. C is any non-zero scalar, and if it was 0, this would have been satisfied also. We're left at y squared is equal to 4x squared, but y squared is equal to 4x squared indeed. Why? Because xy is already in V. So hence V is closed under scalar multiplication. Problem 18. So we have three polynomials, p of x, q of x, and r of x. So that's 2 plus x minus x squared, 3 plus 2x plus 2x squared, and 3 plus 4x plus 16. 3 plus 4x plus 16x squared. The question is, show that R is in the span, of P and Q, which means that R can be written as a linear combination of P and Q, right? Which means that this matrix here consisted of the columns that involve, right, the coefficients of the polynomials as columns. Pay attention to that: 2, 1, negative 1, 3, 2, 2, and 3, 4, 16, right? I have to show that this is going to have a free variable, that these columns are going to be dependent, that the third column is going to be in the span of the first two columns. That means that I will have to have a free variable, or in other words, that the rank has to be less than the number of variables, okay? So 1, 2, 4, I flip the first two rows, 2, 3, 3, negative 1, 2, 16, 1, 2, 4, the second row minus 2 times the first row is 0, 3 minus 4, negative 1, 3 minus 8, negative 5, and then I add row 3 plus row 1, that's 0, 2 plus 2 is 4, and 16 plus 4 is 20. So 1, 2, 4, 0, 1, 5, and then I have 0, 0, 0. Why? Because the last row is a constant multiple of the second row, so they cancel out, right? Row 3 plus 4 times row 2, 4 minus 4 is 0, and 20 minus 20 is 0. So there you go. I have a free variable. This means that I can express the last column as a I can express the last column as a linear combination of the first two columns, which means that I can express this polynomial r as a linear combination of p and q. And here the question stops. If the question was express explicitly r of x as a linear combination of p and q, then I just go one step further. So this is going to be row 1 minus 2 times row 2 is row 1, and I get 1, 0, 0, 2 minus 2 is 0, 1, 0, and 8 minus 10 is negative 2, 5, 0. And from here I can see that the last column, let's say A3, is equal to negative 2A1 plus 5A2, which brings me to the relationship of these vectors, that r of x is equal to negative 2p of x plus 5q of x, and now explicitly it's being shown that r of x is in the span of p and q. We can check that negative 2 times 2 is negative 4 minus 2x plus 2x squared plus 15 plus 10x plus 10x squared, and then I made somewhere a mistake here. So 4 minus 10 is negative 6, my bad, sorry about that. So this is negative 6, so negative 6 here. So that's negative 6 times 2 is negative 12, minus 6x plus 6x squared. Now let's see now what happens. Negative 12 plus 15 is 3, okay? Negative 6, that's plus 4x, good. And then this is plus 16x squared, as we have expected. Okay, and now part B. Part B is, let P to be the vector space of all the polynomials of degree at most 2, okay? Is P of x, Q of x, and R of x a basis for P2? The answer is no. Why? Because in order to create basis, these three vectors P, Q, and R must be independent, but as we have shown in part A, they are not independent, they are indeed dependent.